All right, welcome back to the podcast. Mark, I gotta say, I've been buzzing about something we talked about offline, this whole new way of computing. It sounds kind of wild, to be honest.
Oh, you mean probabilistic computing? Yeah, it's something else, right? It feels like a real fundamental shift, not just, oh, we made chips faster.
Exactly. And what really grabbed me, besides that beauty of uncertainty video you sent me, which was fascinating, was this claim about energy efficiency. Like, we're talking times orders of magnitude better than, say, a power-hungry GPU. Are we talking gaming rig levels of power are now obsolete kind of energy savings?
Well, think beyond just your gaming rig, Jenny. Think those massive data centers doing large-scale AI training, running complex climate simulations, wrestling with huge optimization problems. These things just soak up electricity. Probabilistic computers, or P-computers as they're being called, approach computation in a completely different way. They're actually designed to use thermal fluctuations, that natural noise in materials, to help do the computation. It's about aligning with concepts like the Landauer principle, which talks about the absolute minimum energy needed for a calculation.
Okay, so instead of fighting against that noise, which is what I always thought classical computing was all about, they're actually using time. That feels counterintuitive to everything I was taught about perfect, deterministic computing.
Pretty much. It's a bit of a paradigm flip. The core idea revolves around the p-bit, the probabilistic bit. Unlike a classic bit that's a definite 0 or 1, or even a qubit that's in a superposition of both, a p-bit is stochastic. Its state isn't fixed. It flips probabilistically based on its environment and some parameters you can actually control.
A stochastic nanodevice, leveraging thermal fluctuations. Okay, that's the technical core. Layman's terms, please. How does that translate into solving actual, real-world problems?
Right. So they're excellent at problems that can be mapped onto things like the Ising model. That's a model from physics that's useful for tackling complex optimization problems, sampling, and recognizing patterns, even when the data is incomplete or noisy. Think about trying to find the absolute best routes for a whole delivery fleet under constantly changing traffic conditions, or how to balance a huge financial portfolio under market uncertainty, or even training certain types of machine learning models more effectively when, frankly, your data is a bit messy.
So definitely not something that's going to replace the CPU in your laptop tomorrow, but for these really specific, computationally challenging tasks?
Not yet, no. We're talking about coprocessors, or specialized accelerator systems that work alongside classical computers. But the energy savings potential? It's significant. We're seeing some theoretical benchmarks talking about operations per joule, far exceeding classical systems. Like, the difference between 10 to the 18th power operations per joule compared to maybe 10 to the 12th for classical systems. That's a big difference, too.
Wow. So that almost unbelievable number, the 100 million times more efficient number you hear sometimes, comes from comparing those theoretical thermodynamic limits?
Yeah. That large number likely references the theoretical thermodynamic limit for computation compared to the energy used by current classical approaches. But even the current practical implementations are starting to show really impressive results. Researchers at Purdue, working with Tohoku University, used systems based on these p-bits to solve factorization problems much more efficiently than even a classical supercomputer cluster.
Factorization? Like the core of breaking modern public key encryption? That sounds like a pretty big deal.
Well, for certain types of factorization problems, yes. And the Purdue team saw improvements in both energy consumption and the time it took to find a solution simultaneously. 5. Another promising sign comes from Karim Kamsari's lab at UCSB. They've actually built prototype P computers using readily available, off-the-shelf hardware like FPGAs that are already demonstrating practical advantages.
FPGAs? Like those programmable chips hobbyists and engineers mess around with? So you don't need some incredibly expensive, exotic new fabrication plant just to build these things?
That's a key point, at least for experimentation and early prototypes. You can actually experiment with the architecture and implementation using FPGAs. Kamsari has mentioned that their FPGA prototype suggests that systems with millions of p-bits could become commercially viable for things like optimizing supply chain logistics within maybe 3 years or so. So it's definitely not just confined to theoretical papers. People are building physical systems and seeing what they can do.
Okay, so we've got classical computing, which is our everyday workhorse. We've got quantum computing, which is still out there for many applications, facing huge challenges with things like error correction and just being really difficult to scale reliably right now. And now we have probabilistic computing entering the picture. How do they all fit together in the grand scheme of things?
Good question, and it's not about one replacing the others. Classical is our essential foundation. Quantum has incredible potential for certain very specific problems. Think drug discovery or materials science. But, as you said, it's got a long way to go for widespread use. Probabilistic computing seems to fit nicely into a kind of middle ground. It's showing much greater scalability than current quantum systems. 1. And it's proving to be significantly more energy efficient than classical methods for those specialized optimization and sampling tasks.
Could we see a kind of hybrid system become common, where a company uses its existing GPU cluster for most of its computing, but then offloads those specific, hard optimization problems to a specialized Pico processor?
That's precisely where the thinking is heading. A hybrid approach makes a lot of sense. You leverage the best computing paradigm for the specific part of the problem it's good at. We already see companies like Murex doing this kind of hybrid CPU-GPU thing in the financial industry. You just extend that concept to include probabilistic hardware accelerators.
So, less energy use means a smaller environmental footprint, which is obviously a huge plus in our current climate. Are there any other broader societal implications we should be thinking about as this technology matures?
Certainly. If these kinds of systems become widespread in areas like logistics, finance, and even some aspects of healthcare, we could see significant shifts in the workforce. As automation driven by more efficient optimization accelerates, there will be a need for new skills to manage and program these probabilistic systems. Ethical table. That could mean job displacement in some areas, but also the creation of new roles. On the flip side, the promise of massive energy savings in computing is a pretty compelling environmental story and one of the major drivers for this research.
Definitely. So, what feels like the main hurdle right now, beyond just building those commercial-scale million-p-bit systems that are mentioned?
Scaling up the integration of those p-bits, those individual probabilistic units, reliably and manufacturing them consistently is still a technical challenge. And the software ecosystem is quite young. We need more standardized tools, libraries, and frameworks that make it easy for developers, standard programmers, to easily program and utilize these machines without needing to be a physics expert. There's work happening, like within IEEE, on standardization, which is critical for adoption. Strategic implications table.
It kind of feels like we're witnessing another one of those moments, maybe quiet, maybe not getting the headlines of AI sometimes, but where a genuinely new computing paradigm is emerging, one with the potential to fundamentally change how we approach some of the world's most complex and energy-intensive problems, and doing it so much more efficiently.
It really does. Thermodynamic computing, p-bits, these are definitely terms our listeners are going to be hearing more and more of as this field progresses.
All right, that feels like a good point to wrap up for today. Thanks so much for breaking that down for us, Mark. It's a lot to chew on.
My pleasure, Jenny. Always fun to dive into the future of computing with you.
And thanks as always to our listeners for joining us. We'll be back next week with another look at the tech shaping our world.